Welcome. In this video, we will begin our study of complex numbers, a fundamental topic in higher-level mathematics. By the end of this session, you will be able to define and represent complex numbers on the Argand plane, understand the concepts of modulus and argument, and perform basic operations like addition, subtraction, and scalar multiplication, both algebraically and geometrically. Let's start by considering a familiar problem, solving quadratic equations. We know that for a quadratic equation, ax squared plus bx plus c equals 0, the nature of the solutions depends on the discriminant, delta, which is b squared minus 4ac. If the discriminant is positive, we have two distinct real solutions. If it's 0, we have one repeated real solution. But what happens if the discriminant is negative? For example, consider the equation x squared plus 1 equals 0. The discriminant is negative 4. The quadratic formula gives us x equals plus or minus the square root of negative 1. Historically, mathematicians introduced a new number, I, to represent the square root of negative 1. This number is called the imaginary unit. So we define I as the square root of negative 1. This means that I squared is equal to negative 1. This single definition opens up an entire new system of numbers. Using this, the solutions to x squared plus 1 equals 0 are simply plus I and minus I. These are our first examples of complex numbers. Now that we have the imaginary unit, we can define a complex number in its general form. A complex number, which we often denote with the letter z, is written as z equals a plus bi, where a and b are real numbers. In this form, a is called the real part of z, and b is called the imaginary part of z. We write this as re of z equals a, and I, m of z equals b. It's important to note that the imaginary part, b, is a real number. It's the coefficient of I. This form is also known as the Cartesian form, because it has a direct relationship with the Cartesian coordinate plane. We can plot any complex number z equals a plus bi as a point with coordinates a, b on a special plane called the complex plane, or Argand plane. On this plane, the horizontal axis represents the real part, and the vertical axis represents the imaginary part. This allows us to visualize complex numbers. For example, the complex number 2 plus 3i corresponds to the point 2, 3. The number 4 minus I corresponds to 4 minus 1. A purely imaginary number like minus 3i corresponds to 0 minus 3 on the imaginary axis, and a real number like minus 3 corresponds to minus 3, 0 on the real axis. This visual representation is incredibly powerful and will be a key tool throughout our study of complex numbers. In the complex plane, we can also represent a complex number as a vector. A complex number z equals a plus b. I can be represented by a position vector from the origin to the point a, b. This vector has a starting point at the origin, 0, 0, and an endpoint at a, b. This vector representation allows us to perform operations on complex numbers using vector geometry. For instance, to add two complex numbers, z1 and z2, we can use the parallelogram rule for vector addition. The vector representing z1 plus z2 is the diagonal of the parallelogram formed by the vectors z1 and z2. Let's work through an example to see this in action. Suppose we have z1 equals 4 plus I, and z2 equals negative 1 plus 2i. Algebraically, their sum is 3 plus 3i. Geometrically, we draw the vector for z1 from the origin to 4, 1. Then, from the head of z1, we draw a vector parallel to z2, which goes left 1 and up 2. The resulting vector from the origin to the final point, 3, 3, represents z1 plus z2. Subtraction and scalar multiplication work similarly. For example, to find z1 minus z2, we add z1 to the negative of z2. To find 2z1, we scale the vector z1 by a factor of 2. A special operation on complex numbers is the complex conjugate. The complex conjugate of z equals a plus bi is denoted by z star, and it's defined as a minus bi. We simply change the sign of the imaginary part. Geometrically, the conjugate z star is a reflection of z across the real axis. If z is at the point a, b, then z star is at the point a, b. This reflection is a key property of the conjugate. The conjugate has several important properties. Let's explore two of them. First, the sum of a complex number and its conjugate is always a real number. If z equals a plus bi, then z plus z star is 2a. The imaginary parts cancel out. Second, the difference between a complex number and its conjugate is always a purely imaginary number. Z minus z star is 2bi. The real parts cancel out. These properties are very useful in solving problems and proving theorems involving complex numbers. Now, let's move on to the modulus and argument of a complex number. These are two of the most important concepts in this topic. Since we can represent a complex number as a vector, it makes sense that it has both a magnitude and a direction. The magnitude is called the modulus, and the direction is called the argument. Let's start with the modulus. The modulus of a complex number z equals a plus bi is the length of the vector from the origin to the point a, b. We denote it with vertical bars, like absolute value, and it's calculated using the Pythagorean theorem. The modulus of z equals the square root of a squared plus b squared. The modulus represents the distance of the complex number from the origin in the Argand plane. For example, if z equals 3 plus 2i, its modulus is the square root of 3 squared plus 2 squared, which is the square root of 13. This means the point, 3, 2, is at a distance of root 13 from the origin. The modulus has several key properties that are essential for HL problems. First, the modulus of the conjugate is the same as the modulus of the original number. Second, the modulus squared is equal to the number times its conjugate. This is a very powerful identity. Third, the modulus of a product is the product of the moduli. And fourth, the modulus of a quotient is the quotient of the moduli. These properties allow us to manipulate and simplify expressions involving moduli without having to convert back to Cartesian form every time. Now let's discuss the argument, which describes the direction of the complex number. The argument of z, written as arg z, is the angle theta measured counterclockwise from the positive real axis to the vector representing z. Since adding 2 pi to an angle results in the same direction, there are infinitely many possible arguments. To make it a function, we define the principal argument. The principal argument is the unique angle theta that lies in the interval from negative pi exclusive to pi inclusive. This is the standard convention in IB mathematics. To find the argument, we use trigonometry. For z equals a plus bi, we can form a right-angled triangle with sides a and b. The tangent of the angle in this triangle is b over a. However, we must be careful. The tangent function has a period of pi, so tan inverse of b over a will only give us an angle in the first or fourth quadrant. To find the correct argument, we must first determine the quadrant in which the complex number lies. Let's find the argument of z equals negative 1 plus 3i. First, we find the reference angle, phi, using the absolute values of the real and imaginary parts. Tan phi equals 3, so phi is approximately 1.25 radians. Next, we plot the number. Negative 1 plus 3i is in the second quadrant. The principal argument, theta, is pi minus the reference angle phi. So the argument is approximately pi minus 1.25, which is about 1.89 radians. Always remember to plot the complex number first to determine the correct quadrant and adjust the angle accordingly. Let's work through a more complex example that combines these ideas. Suppose we are given that z equals a minus I, where a is a real number, and the argument of z is negative 5 pi over 6. We need to find the exact value of a. First, let's analyze the given information. the argument is negative 5 pi over 6. This angle is in the third quadrant. An angle of negative 5 pi over 6 means we rotate 5 pi over 6 radians clockwise from the positive real axis. This places our complex number in the third quadrant. Now, let's look at the complex number itself. Z equals a minus I. The imaginary part is negative 1. For the number to be in the third quadrant, the real part, a, must be negative. So we know that a must be a negative number. This is a crucial piece of information that will help us find the correct answer. We can use the tangent function to relate the argument to the real and imaginary parts. The tangent of the argument is the imaginary part divided by the real part. So tan of negative 5 pi over 6 equals negative 1 over a. Now we need to evaluate tan of negative 5 pi over 6. The tangent of negative 5 pi over 6 is the same as the tangent of pi over 6, which is 1 over the square root of 3. Since the angle is in the third quadrant, where tangent is positive, the value is positive 1 over root 3. We can now set up our equation. We have 1 over root 3 equals negative 1 over a. Solving for a, we get a equals negative root 3. This matches our expectation that a must be negative. So the exact value of OSO is negative root 3. This example shows the importance of combining algebraic and geometric reasoning. Let's look at another common type of problem, finding the modulus of a complex number defined by an equation. Consider the equation 3 times the modulus of z plus 1 equals the modulus of z plus 9. We need to find the value of the modulus of z. The key to solving this is to use the property that the modulus squared is equal to the number times its conjugate. This property, squared equals z star, allows us to convert an equation involving moduli into an algebraic equation involving z and z star, which is often easier to solve. First, let's square both sides of the given equation to get rid of the modulus signs. Squaring both sides gives us 9 times the modulus of z plus 1 squared equals the modulus of z plus 9 squared. Now we apply our key property to both sides. This gives us 9 times the quantity z plus 1 times its conjugate, which is z star plus 1, equals the quantity z plus 9 times its conjugate, z star plus 9. Next, we expand both sides of the equation. Expanding the left side gives 9 times z star plus z star plus 1. Expanding the right side gives z star plus 9z plus 9z star plus 81. Now, we distribute the 9 on the left side. This gives 9z star plus 9z plus 9z star plus 9 equals z star plus 9z plus 9z star plus 81. We can see that the terms 9z and 9z star appear on both sides, so they cancel out. This leaves us with 9z star plus 9 equals z star plus 81. Now, we can solve for z star. Subtracting z star from both sides gives 8z star plus 9 equals 81. Subtracting 9 gives 8z star equals 72. Dividing by 8, we find that z star equals 9. Finally, we use our key property again to find the modulus. Since z star is equal to the modulus of z squared, we have the modulus of z squared equals 9. Taking the square root, we find that the modulus of z is 3. We take the positive root because a modulus, being a distance, must be non-negative. This method of squaring and using the conjugate property is a powerful technique for solving equations involving moduli. Let's recap what we've covered. We've learned to define complex numbers in Cartesian form, represent them on the Argand plane, and understand the concepts of modulus and argument. We've seen how to perform basic operations like addition and subtraction, both algebraically and geometrically, and we've explored the properties of the complex conjugate and modulus, which are essential tools for solving more complex problems. You are now equipped to tackle problems involving the representation and basic properties of complex numbers. In our next session, we will explore the geometry of complex numbers in more detail, including distances, midpoints, and transformations. To solidify your understanding, here are 5 practice questions in the style of IB Mathematics HL. Pause the video and try to solve them on your own before watching the solutions. Question 1. Let z equals 2 minus 3i. Find the modulus and principal argument of z. Question 2. Given z equals 1 plus I and w equals 2 minus I, find the complex number u equals z squared plus w dash star. Question 3. Find the exact value of the real number a such that the argument of z equals a plus 2i is 2 pi over 3. Question 4. Find the modulus of z given that 2 times the modulus of z minus 3 equals the modulus of z plus 6. And question 5. Show that for any complex number z, z plus z star is always a real number. Let's go through the solutions. Here is the solution to question 1. For z equals 2 minus 3i, the modulus is the square root of 2 squared plus negative 3 squared, which is the square root of 13. To find the argument, we first find the reference angle phi. Tan phi equals 3 over 2. Since z is in the fourth quadrant, the principal argument is negative phi. So the argument is negative arctan of 3 over 2. Here's the solution to question 2. We need to find u equals z squared plus w dash star. First, let's calculate z squared. Z squared is 1 plus I squared, which expands to 1 plus 2i plus I squared. Since I squared is negative 1, this simplifies to 2i. Next, we find the conjugate of w. W star is 2 plus I. Finally, we add the two results. U equals 2i plus 2 plus I, which gives us 2 plus 3i. Here is the solution to question 3. We are given that the argument of z equals a plus 2i is 2 pi over 3. This angle is in the second quadrant. For z to be in the second quadrant, the real part, a, must be negative. The imaginary part is positive 2. We use the tangent function. Tan of 2 pi over 3 equals 2 over a. Tan of 2 pi over 3 is negative root 3. So, negative root 3 equals 2 over a. Solving for a, we get a equals negative 2 over root 3. Here is the solution to question 4. We need to find the modulus of z given the equation 2 times the modulus of z minus 3 equals the modulus of z plus 6. We square both sides and use the property that the modulus squared is the number times its conjugate. This gives us 4 times the quantity z minus 3 times z star minus 3 equals the quantity z plus 6 times z star plus 6. Expanding both sides gives 4 times zz star minus 3z star plus 9 equals zz star plus 6z plus 6z star plus 36. Distributing the 4 and rearranging the terms to one side, we get 3zz star minus 18z minus 18z star equals 0. Dividing by 3, we have zz star minus 6z minus 6z star equals 0. This equation represents a circle. To find the modulus, we need to find the center and radius. We can rewrite the equation as the modulus of z minus 6 squared equals 36. This is the equation of a circle centered at 6 with a radius of 6. The modulus of z is the distance from the origin to the point z. The smallest modulus is 0 and the largest is 12. The question asks for the modulus, implying a single value. This usually means the radius of the circle, which is 6. Finally, here is the solution to question 5. We need to show that z plus z star is always a real number. Let's start by defining z in its Cartesian form. If z equals a plus bi, then its conjugate z star is a minus bi. Now let's add them together. Z plus z star equals a plus bi plus a minus bi. The imaginary parts, plus bi and minus bi cancel each other out. The result is 2a. Since a is a real number, 2a is also a real number. This proves that the sum of any complex number and its conjugate is always a real number. That concludes our introduction to complex numbers. We have established the foundational concepts of the Argand plane, modulus, and argument, and practiced applying them to solve problems. You should now be able to confidently represent complex numbers, calculate their modulus and argument, and use the properties of the conjugate and modulus to solve equations. These skills are crucial for the more advanced topics we will cover in the future. Thank you for watching. Keep practicing these concepts, as they are the building blocks for your success in this chapter.